Hey, this is Bladum, and today, surprise, surprise, we're going to be talking about game theory. But actually, surprise, um, this is the last theory video. I believe it's number 7. After this, there will be no more theory. We'll be done. So today I'm going to talk about something very, very important, and that's the indifference principle. So, this is a statement of truth, and it's very useful because it's going to give us what we need to be able to compute Nash equilibria. And of course, last time we talked about why we would want to do that. So the indifference principle, it's a statement of truth, and the statement is as follows. So suppose that S naught, Z naught is a Nash equilibrium, and that S naught is a mixed strategy, and it mixes pure strategies S1, S2, dot, 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 Sn. And we're only going to count the pure strategies that it mixes between, that it actually mixes between. So each with non-zero probability. So don't count the things that it doesn't actually mix between. So for example, Marge's rock, paper, scissors strategy of 2/3 paper, 1/3 scissors, the pure strategies it mixes between are always throw paper and always throw scissors. It doesn't mix between always throw rock though. So suppose that S naught, this strategy that appears in the Nash equilibrium, mixes between pure strategies. Then the conclusion is that S1 through Sn, they all have the same expected value against Z naught. And this should be a little bit surprising. So I encourage you to pause the video and to consider why this is true. Alright, so why is this true? Well, one way that we've sort of toy modeled mixed strategies is you set out your pure strategies and you give probabilities for that you're going to play each of them. And then you go into random.org, you generate a random number, and you use that to choose the pure strategy you're going to play. So suppose, and this is, suppose that the EV of S1 is less than the EV of S2. And here you might say, well, what if the EV of S2 is less than the EV of S1? Well, the labels are completely arbitrary. I haven't said anything about S1 beyond this statement. So as long as two of the EVs are not the same, just shuffle around what you call them until the EV of S1 is less than the EV of S2. So this is, log without loss of generality. We can assume that the EV of S1 is EV than that the EV of S1 is less than the EV of S2. Then the question is, why would you ever play S1. So you go into random.org and it generates S1. It says right now you should play S1. And you know against your opponent's strategy of Z0 that S1 does worse than S2. Wouldn't you be better off just playing S2 instead? And the answer is yes, you would. So you shouldn't ever play something that has worse EV when you could just play something that has better EV in that exact same situation. So you wouldn't. So what that means is that, so remember that we're at a Nash equilibrium, right? S0, Z0 is a Nash equilibrium. And what that means is that S0 is maximally exploiting Z0. So your EV of S0 is maximal. But look, S0 mixes S1 in some of the time. With non-zero probability, it plays S1. And you could improve your EV by just playing S2 whenever random.org told you to play S1. So that means that S0 wouldn't be maximally exploitative. And this is a contradiction. So this standard symbol for contradiction is this broken arrow thing. And that's the end of the proof. So to recap, if you're mixing between strategies and one of your pure strategies does worse than the rest, it says worse EV, then whenever random.org tells you to play that, just play a different one and you're improving your EV. So if your EV is already as high as possible, because you're at a Nash equilibrium and you're maximally exploitative, then what that means is that all the EVs of the pure strategies have to be equal. Otherwise, you would get this contradiction. And so that's the indifference principle. So again, the indifference principle is this, and this is very important, so I'm going to box it. So the indifference principle is very useful because it lets us calculate Nash equilibria. And I'm going to do an example of that in the next video. So I guess I'm going to call that video theory, and I lied that this was the last theory video. The next video is the last theory video.